If not, we can take our Q&A session now. Sabri was mentioning some hack committee questions earlier that you want to discuss on Q&A.
Yes, Dania, I was hoping that all of our speakers could participate in this, like sort of like a roundtable discussion.
Yeah.
And also users, the participants might have certain insight about the questions themselves. Like there might be some people who are more experienced than the question than us even. So I welcome everybody to participate. Would you like to lead the discussion, Dania? Or?
No, you carry on, Sabri. And I hope Radovan, Ulle, and Marcinas are here. Yeah.
Yes.
Yes.
So yeah, first Ulle Vidar work with us, right? So sometimes he has this controversial things that he say. So the best discussions we had were in like the corridors. He would ask me, what is the minimum amount of data you could fit in a RAM? Then he would ask like, what is the difference between serial and parallel? Certain questions. So the best knowledge that the wisdom I got from Ulle Vidar is like when you have like a relaxed question, not a specific one. So I'm going to sort of challenge something he said to get more out of him. Sorry, Ulle Vidar. I don't.
No, I just want to. I just want to point out that Marcin is always disagreeing with me. Yes. And that makes it very hard because I have to really pinpoint my.
That's not true.
Oh, it's quite often. So it's really good. I mean, I would rather spend time with you than many people who say just yes, minister. So yes. The good thing is that if you disagree with me just by principle, I have to really displaying it very nicely and thoroughly.
Yes.
Yeah. So yes, come on with the question.
Yes. So I'm going to challenge one of the examples about disk I/O, right? So you are using this Bergen example, like whether you are going in the direction of the heavy traffic or with the direction less traffic. So I'm going to challenge that example, and I would say that example doesn't fit for this scratch and local scratch. An example that would fit maybe like highway versus old E6, for example, like a smaller road versus larger road. It's not the traffic direction in this case. How would you defend yourself?
No, my point is that if you go from Oslo to Norway going east, it's far longer. It's about 40,000 kilometers. If you go the other way, it's only a couple of hundreds. So the disk I/O is, if you do random access, this is by physical nature. I mean, I used an example with a tape. A disk, spinning disk and a tape is exactly the same thing. And I can tell you that I am not comparable to Einstein. And for those of you can look up Einstein and the wireless telegraph and the cat. I don't want to share that story, but you can look it up. Anyway, it's use a tape as a storage media, and the disk is the same thing. It's a magnetic media that spins around. A tape is a magnetic media. You load the tape and you rewind the tape and you open the file at the beginning of the tape. So I want to write at sector 128. So I have to run the tape forward using a seek command and run the tape forward 128 sectors. And normally the tape runs quite rapidly there, and that you see on the spinning tapes on all films and such. So it takes some time to spin the tape up until that. Then you place the head and you read the sector at number 128. You read the data there, 512K or something. Or half a kilobyte, 512 bytes, or whatever the block size is. And then the next random read, it's 2 million blocks away. So I have to spin the tape forward quite a long time to get there. And then I place the head and then I can read there. Then there is another one requesting 48. So I have to spin the tape back. This is random access. If you use a disk or a tape, it doesn't matter. It's the same problem anyway. It's really bad. But if you are doing on a memory-based disk, first of all, a memory-based disk is not a memory. There are memory chips that hold the data, but the machinery that you talk to the disk is like a database. You come with some data, and I want to place this block of data on your disk, on a solid state disk or memory disk. And then the machinery put it somewhere and gives back some kind of hashing algorithm, some kind of key. And the next block you could put it somewhere else on then, and you get some hashing table that each block has some kind of address. So it's more like a solid state disk is more like a database than a tape. And the speed of this machinery, how rapid it can do, has something to do with the quality of the solid state disk. So poor solid state disk has poor controller, and they are generally much cheaper than the better one, who has better controllers and are generally faster. So but in principle, you have random access on a solid state disk, far better than and the only thing that limits the speed is how fast the transaction machinery can retrieve the data to you. Was that okay, or was it?
Yeah. Thank you, Olavidar. So, Maharashi, we have SRun, MPI run, and MPI-X, for example. So we have some recommendations to use SRun on Saga and From, for example. Is there any specific reasons for this?
Why we use SRun or MPI run?
Yes.
Well, SRun we want to use because it's integrated into the job scheduling system. So technically, it should maybe run a bit faster, but I would say it doesn't really make any difference. You can use either MPI run or SRun, whatever suits you more. I personally mostly use MPI run, but it's supported. Both of those things are supported.
Thank you, Marcin. And there is a raised hand, Thomas. Yeah.
Hi, thanks. Can you hear me?
Yeah.
Yeah. I was wondering about this NUMA awareness, and maybe Marcin can answer this. Is that specific for OpenMP, or is it also OpenMPI that is important?
So whenever you start an MPI program, it will, so MPI ranks are processes, and they are started on a certain CPU. And where they are started is managed by, for example, SRun or MPI run. Those will kind of bind the ranks to a given CPU. And from that moment, by default, when you allocate this memory, it will be allocated only, let's say, on the memory banks close to that CPU. So in this sense, when you run pure MPI codes, you don't have to do much more. This NUMA awareness will most likely be there. Where it's important is for threaded codes, where threads actually share the data between each other. There you actually have to make sure that you do it correctly, and you have to be more specific about it, or more explicit. You have to do it yourself, otherwise things can go wrong.
Okay, yeah, thanks.
So Danya, interrupt me if somebody else want to ask a question.
Yeah, of course.
Yeah. So Radovan, when you're showing this your examples, those were not really using any IO, right? So is there any comment about, let's say, a program is trying to write to files, and you want to sort of use parallelization? How would you sort of like we actually didn't touch upon it much? How would you prevent sort of some threads waiting to write to files, for example? Is there any technique that you personally know?
And he is speaking as the person writing the code, or as a person running somebody else's code?
As a person writing the code, maybe. Yeah. Like, how would you prevent that you write your code in a way that is very parallel, but some of them threads actually waiting to write to a file, sort of.
So what I normally do and recommend to do is to.
Is it me, or Radovan is not audible to me? It is just me?
Another
Yeah.
one is very low.
Yeah.
Is it better now?
Yes, yes.
Okay, I was trying to adjust because I got somewhere else the feedback that the sound quality is really bad. So I tried to adjust and I think I adjusted the wrong way. So good. Okay, so thanks for the question. So when I program parallel code, what I try to normally do is that only one task does the writing and reading. If possible. I mean, it may not be possible because depending on what you do, depending on the algorithm, maybe they need to read and write different things, but I try to keep it simple. And all the tasks, they do their work. They communicate it back to the sort of, I don't know, manager. So the task 0, the rank 0, and it's the rank 0 that does all the reading and writing. And that's a starting point. I think the other comment that I would like to give on this question, but also the previous questions, is that it can feel a little bit scary because now we heard about all the horror stories of what can go wrong in disk I/O and in network and all the things to think about. I would still, both in programming and when using somebody else's code, I like to start very simple, try a few things out, and then measure where is the problem. Maybe there is no problem and then there is nothing to be optimized. So try to find out, is there any problem with disk I/O? Is there any problem with network? Is there any problem with memory access? And we have tools for that. One tool that was mentioned was this vTune. Another tool that was mentioned, but unfortunately I didn't show it, is this ARM performance report. And these tools can give you, they can tell me, is there a problem with I/O, network, or communication, or memory? And then when I know, then at least I know that I don't have to worry about the other things. I can keep it simple. And then if I don't know what to do about it, I can approach the support and ask, please help me. I see this. I don't know why. What can we do about it?
Thank you, Radovan. So the next question is about N tasks and CPUs per task. Who of our colleagues would be willing to give an idea about that? Whether we should ask N tasks or CPUs per task when you're asking number of cores. Maybe Ulla want to say something about it?
I can. I had some of this on my slide, but the CPUs per task is for the threaded program, the OpenMP programs, which sets this variable OMP number of threads. And N tasks is setting the number of MPI ranks. So you can ask for only, don't bother about the node, you can only ask for some systems. It's a little bit dependent on whether or not you are running on Saga from a Betsy. But in principle, you can ask for N tasks. Let's say you put N tasks as 1000. And then you can say CPUs per task, let's say 128. That will take most of Betsy, because it will schedule 128 OMP ranks per node and 1,000 nodes. No, 1,000 tasks. Sorry, 1,000 tasks, not 1,000 tasks.
Yes,
So that will mean 128,000 cores together. But it's not so simple to explain it just in orally. It's better to look on the examples and try it out yourself.
If I can comment on that, so for me, CPU per task, I mean, I know what it does, but it's not an intuitive name. I wish this thing was called threads per task. Then I would know what it is. I think it just sounds confusing. Of course, we didn't choose it. Somebody else chose these names. But I like to think of CPUs per task as threads per task. I don't know whether this was helpful or not.
Yeah, I totally agree, because it is actually threads. So, but it's important that it sets this variable OpenMP num threads. So I agree with you, Radvan. It's very good.
So yeah, it's a good point as well, because in general, in some of the questions, although it's not asked directly, I see this point. Like on our HPC systems, we only have hardware cores. We don't have this virtual threading, right? But programs, they use threading. So can someone explain a little bit about what this hardware core and what a thread is?
A thread is a string of instructions. And when you have a huge amount of threading, like in the GPUs, they had to get the terminology from weaving, like a warp and so on. Warp is all the fixed threads on a weave. But we are not faced with that many threads. But a thread is a string of instructions, and for normal jobs that are not the accelerated jobs, normal CPUs, a string, we have only a few strings. And if that string of threads contains HPC instructions, they can only use part of the machinery inside the core. If we are running something else like we don't, then it might be beneficial to schedule two strings of threads, two strings of instructions into the same core, so that you can use both the integer and jump units and predictive units and the floating point units simultaneously. But in HPC, we are generally running, all the thread streams are exactly the same. Hence, we can only schedule one stream per core. And looking from the outside, they say that there are two cores. They are actually virtual cores. It's just the thing that it can accommodate two streams of two threads with streams of instruction at the same time. But this is like just like braiding, and when two car lanes go into one, because there are only one set of floating point machinery. Well, to make it short, there are more than that, but they assume that there is only one set of floating point machinery, and then two threads come into there, and you have to braid them, so two comes into one, so they will take one each other, and the throughput is exactly the same as if we were having only one. But that only applies to very structured problems like HPC. If you are running a web server, it's quite often beneficial to use schedule two threads per core.
So to add to the confusion, what does the word hyperthreading means?
Oh, this is something that Intel invented. They say that you could run two threads, and in the early days there wasn't really that good threading because the machineries were not really that complex as it is today. So I think it should be avoided to use the hyper threading, but it's actually more than one thread per core, which is the hyper ones.
So
I usually like to use the virtual cores because they look like cores, but they are not. Like a virtual machine, it looks like a machine, but it isn't.
Marcin, are you still around?
I think so, yeah.
Yes. So another thing that we didn't talk much about is the interconnect, the connection between the compute nodes. So we have heard like once in a while something called InfiniBand, for example. Is there anything specific that you want to specify during running programs in order to use faster network between nodes? Especially in a program that will use multiple nodes.
Yes, so that's only relevant for MPI programs that communicate over the InfiniBand. And the good answer is no, you don't have to do anything. The OpenMPI or the MPI libraries on the machines are already configured in such a way that they will use InfiniBand. So everything should already be, let's say, optimal, right? You can of course have problems, but those would usually be kind of application issues, how you do the communication, who communicates, who sends data to whom. Maybe it's too much, maybe it doesn't scale, but technically you don't have to do anything to use the correct interconnect.
Okay.
Do you have more time or?
I would like to wrap up on time because it's been 4 hours, so I don't want to test anyone's patience now. So thank you for today and all the instructors who has done a fabulous job and who were our helpers on the HackMD. So I would like to thank you all.